Okay. All right. So let me start by recalling where we finished. So we finished with the Hessian comparison theorem. Which gives you, so just 1 second. Yeah. So the Hessian comparison theorem gives you upper and lower bounds on the Hessian of the distance function from a point P. So d sub P, this function, on a geodesic ball. So what we found is that if the sectional curvature on the ball is bounded above by some negative constant minus a squared and bounded below by minus b squared, then the Hessian of the distance function. So remember, this is a bilinear form. So if you look at it on the diagonal, it's a symmetric bilinear form. So it's determined by its values on the diagonal, w comma w. So that's a quadratic form. So that quadratic form is bounded below by a cot h ar, a constant times the normal component of w, norm squared, where here this normal component means so w is a tangent vector at a point q in the ball, which is different from p. And so then you have a unique geodesic from P to Q. And so the normal component means the component of this tangent vector, which is normal to the geodesic passing through Q, starting from P. All right. Okay. So we have these upper and lower bounds on the Hessian of the distance function. Okay. So first of all, note what this means, that the Hessian of the distance function, this is a positive semi-definite, right? Yes?
Yes. Yes.
Yes.
Positive semi-definite. Okay. And this actually leads to the fact that geodesic balls in negative curvature, they are strictly convex. Okay. It leads to the fact that geodesic balls are actually strictly convex. So let me explain a bit. So geometrically, what is the meaning of this Hessian? Actually, this gives us curvature of the geodesic sphere in the direction of W. So let me explain that. So we have the center of the ball P, and then I'm taking a point Q in the geodesic ball. Okay. So we already saw that if I take the geodesic from P to Q, then this is orthogonal to the geodesic sphere, right? That's the Gauss lemma. Yes. So this is the geodesic sphere of radius r around P. And so if this geodesic is gamma, then say that r is equal to the distance of P from Q, right? So this tangent vector is gamma prime r, right? If gamma is unit speed, let's say, okay, right?
Yes.
And this is, we saw that this is the same as the gradient vector to the distance function at the point Q, right? Okay.
Yes.
So what does this mean? This means that if I look at the gradient vector field restricted to this sphere S, right, then this is equal to the unit normal vector field, the outward unit normal. This is the outward unit normal to the sphere S. Yes?
Yes.
Okay. And when we're looking at the Hessian of the distance function, so say at the point Q, right, where does this go from? So this goes from the tangent space at Q to the tangent space at Q, right? How is this defined? This is defined by W goes to nabla sub W of the gradient vector field, right? Yes? This is the definition of the Hessian as a self-adjoint linear map, right?
Yes.
Yes.
Now, if W is tangent to the geodesic, right, in the tangent direction, the gradient vector field, its covariant derivative will be 0, right? Because this gradient vector field is just gamma prime. Restricted to the geodesic is just gamma prime. So this just becomes nabla gamma prime, which is 0, because gamma is a geodesic, right? Okay.
Yes.
Yes.
So the Hessian of dp at Q, this maps R gamma prime to 0, right? Okay. But now this is a self-adjoint linear map. So it maps the orthogonal complement of gamma prime to the orthogonal complement of gamma prime, right?
Yes.
Yes. This is just linear algebra. If a
Yes.
self-linear map sends a subspace V to itself, into itself, if T of V is contained in V, then T of V perp is contained in V perp, right?
Yes.
Yes. Okay. So therefore, so this is contained inside R gamma prime, and Hessian, this is self-adjoint. So this means that the Hessian TPQ, this maps R gamma prime perp into itself. So it defines an endomorphism of the orthogonal complement of the geodesic. This is just the tangent space to the sphere, right?
Yes.
This is to the sphere. Okay. So, so if I restrict the Hessian to the so let yeah, so so let T be the operator, which is the Hessian restricted to the tangent space to the sphere. So this goes from TQS to TQS. right? And what is this operator? It's just W goes to nabla sub W of grad dp. And this I can write as nabla sub W of n, right? Where n is equal to grad dp restricted to S, which is the outward unit normal, right?
Yes.
So this operator on the tangent space of the sphere, this is what is called the shape operator. This is called the shape operator of the sphere. So why is it called the shape operator? Because it measures how much the outward normal, the unit normal to the sphere is bending, right? How much it is changing at a point, right? We're looking at the derivative of the normal in different directions, W, right? Okay.
Yes.
So that tells you how much the geodesic sphere is curving, right, at a point. So if this is a part of the sphere, okay, then so suppose this is the normal, okay. So and say W is a tangent vector to the sphere. Then what is this covariant derivative? Nabla sub W of n. It means you move, so this, let's say this is a curve in the sphere, which is tangent to W at the point Q, okay? Then what it means is, you look at the normal vector along this curve, right? And look at its covariant derivative. Now, what is the covariant derivative geometrically? What it means is, you parallel transport this vector back to Q, right? You parallel transport it back, and then
Yes.
look at the difference here. Look at this difference,
Right.
right?
Yes.
So,
yes.
so if this distance is, say, of order t, where t is tending to 0, then this little vector here, this will be basically t times nabla w n plus little o of t. Is
Yes.
this clear? Okay, so geometrically, this is the covariant derivative. So if this, if it's a small sphere, right, then the normal vector will bend faster, right? Is it clear? This
Yes, sir.
covariant derivative will be larger.
Yes.
Whereas if it's a large sphere, then the normal vector will not change too much, right? Okay.
Yes.
Okay. So this change in the normal vector is basically giving you the curvature of the sphere. Okay. So how do you measure the curvature? Well, what do you want to look at? You want to look at this change in the normal vector and then the component of the change in the direction of W, right? So if I want the component of the change in the direction of W, then I look at the following quadratic form, B of WW. So this is the inner product of nabla Wn with W. Is it clear?
Yes.
Yes.
So this is what is called the second fundamental form of the sphere, this quadratic form. So this measures how much the sphere is curving in the direction of W. Okay.
Yes.
this quadratic form. Okay, so it comes from a bilinear form. B of WV is inner product nabla Wn with V, right? That's the bilinear form. It's the bilinear form associated to the shape operator, right? Is it clear?
Yes, sir.
Okay, so this is the quadratic form. Associated to the self-adjoint shape operator. Okay. Now, what we've done here for the sphere, so what is the Hessian? The Hessian is nothing but the Hessian of the distance function, or if I look at as a quadratic form, it's nothing but the second fundamental form of the sphere, right?
Yes.
Okay.
Yes.
Okay. So yeah, and as a linear map, it's just the shape operator of the sphere. The Hessian of the distance function is just the shape operator of the sphere. Okay. And so what we're getting, you see, the Hessian comparison, if W belongs to TQS, which is the orthogonal complement of gamma prime, then W is equal to its normal component, right? And so the Hessian comparison theorem just tells us that A cottage AR norm W squared less than or equal to nabla squared dp WW, which is equal to inner product TWW, right? Where T is the shape operator. Yes?
Yes.
Yes.
Less than or equal to B cottage BR norm W squared. Okay. Is this clear? So this, what does this mean? The quadratic form associated to the linear map T, the self-adjoint linear map T, it's bounded above and below by positive constants times norm W squared, right? Okay, so this means that the eigenvalues of T, right, are bounded above and below by this A cottage AR and B cottage BR, right?
Right.
Okay, so implies A cottage AR less than or equal to lambda min less than or equal to lambda max less than or equal to B cottage BR. Okay, so this shape operator is positive definite, right? Okay, now it's positive definite. It's not just positive semi-definite. It's positive definite because we've restricted to the tangent space to the sphere.
Right.
There it becomes positive definite. Is this clear? Yeah.
Yes, sir.
Now this is positive definite. Okay. And you have upper and lower bounds on its eigenvalues. And the eigenvalues lambda 1 to lambda n minus 1 of the shape operator these are called principal curvatures of the geodesic sphere S. Okay. Is this all right?
Yes, sir.
Okay. Yeah, so the eigenvectors of the shape operator, those correspond to directions where the change in the normal is proportional to the direction you're moving in, right? Okay. So for example, if you take an ellipsoid in R3, right, then if I take this point here, then the eigenvectors of the shape operator will be this direction and this direction. Okay. This is the normal vector. These will be the eigenvectors of the shape operator. Does this make sense?
Yes, sir.
Yeah, this you can, I mean, intuitively, it's clear these should be the eigenvectors of the shape operator, right? I'll think of a proof, but I mean, intuitively, this should be clear. Okay, in these directions, the change in the normal vector is proportional to the vector, all right? And the principal curvatures are positive, so, okay. So what we did here for the geodesic sphere, we can do for any submanifold of codimension 1, right? That means any submanifold of dimension n-1, right? So then the tangent space to the submanifold is of dimension n-1. Its orthogonal complement is one-dimensional. So up to sign, there's a unique unit normal vector at each point, right? Okay.
Yes.
So then you do the same thing that we did here. You define the shape operator by taking a unit normal vector field on the submanifold S, and then your shape operator is just W goes to nabla W of n. Is it clear? This will go from the tangent space to the submanifold to itself. Is this clear?
Yes, sir.
Yes.
Okay. And see, if the submanifold, so, okay, so similarly, so let me just write that. Similarly, oh, okay, wait. Before that, let me just note, in this case, for the sphere, what is the Hessian comparison theorem telling me, therefore? It's telling me a few things. So first of all, what does this look like when R is small? So let me look at this inequality star. So look at the inequality star. For R tending to 0, then the left-hand side, cot h AR just looks like 1 over AR, right? Yes?
Yes, sir.
Cot h x looks like 1 over x for x small, right? So this becomes A times 1 over AR. Okay. Into whatever, norm W squared. Into a term which is 1 plus little o of 1. Okay. This is less than or equal to inner product TWW less than or equal to B into 1 over BR norm W squared into 1 plus little o of 1. Okay. So the A and the A cancel, the B and the B cancel. So this looks like 1 over R into norm W squared, right? Okay.
Yes.
Yeah. And that is the same 1 over R into norm W squared. That is the same as the curvature of a sphere of a Euclidean sphere of radius R.
Yes.
Okay, that will be the same as the principal the curvature of a Euclidean sphere of radius R. All right. That will be the principal curvature of a Euclidean sphere of radius R. So what does that mean? That means that geodesic spheres, when R is small, they look like Euclidean spheres up to second order. Right? Curvature is involves second derivatives, right? So it's a second order quantity. Up to second order, Euclidean geodesic spheres look like Euclidean spheres when R is small. Okay? Does this make sense?
Yes.
All right. Yeah. So they look like Euclidean spheres. Okay. Now, what happens when R is large? Well, you know that in Euclidean space, as the radius of the sphere goes to infinity, the curvature goes to 0, right?
Yes.
Okay. But that does not happen in negatively curved manifolds. So here our manifold is negatively curved, right? The sectional curvature is bounded above by a negative constant minus a squared. And it's bounded below also by another negative constant minus b squared. Here what happens? For R tending to infinity, what do you get? Cot h tends to 1, right? As x tends to infinity, cot hx tends to 1, right? So you just get in the limit a into 1 plus little o of 1, a into norm W squared into 1 plus little o of 1 less than or equal to inner product TWW less than or equal to B into norm W squared into 1 plus. So what does this mean? This means that in a negatively curved manifold, even as the radius of geodesic spheres tends to infinity, their curvatures are bounded below by a positive constant. So the curvatures do not go to 0. You see? Okay. Is this clear?
Yes, sir.
Yes.
I mean, how to see that geometrically?
So in case
Okay.
of hyperbolic plane, I can see that that's happening.
Well, see, what happens is, so what happens to large spheres? So this brings us to horospheres. So what are horospheres? Okay, so since we're talking about this, since we're going to be talking about horospheres anyway. So for simplicity, let me suppose M is a Hadamard manifold, okay? So that means complete, simply connected, non-positive curvature, okay? All right. Okay, yes. So it's diffeomorphic to Rn, right? The exponential map is a diffeomorphism by the Cartan and Hadamard theorem. Now, so if I take a point P in M, then I have a distance function dP which is defined on all of M. It's smooth on M minus a point. Okay. Now, what I want to do is, so the level sets of dP are geodesic spheres centered at P. Right. Now, what I want to do is, I take a geodesic, let's say a geodesic ray, gamma. So this means that this is an isometric embedding. Okay, this is an isometric embedding of a half line into M. So the distance gamma S gamma T is equal to mod S minus T for all ST. Okay. Now what I do is I take P, the center of my distance function, I take P to be gamma T. Okay, you let P be gamma T and you let T tend to infinity. Okay, then what happens to these functions D sub P? Well, of course, they're going to tend to infinity, right? If P is, this is my geodesic. Okay, this is P equal to gamma T. And let me call the starting point of the geodesic, say O. This is an origin, O equal to gamma 0. Okay. So if I take any point Q here, then of course the distance from P to Q is going to go to infinity, right?
Yes.
Yeah. So dP tends to plus infinity on all of M. So we can't take a limit of these distance functions as such, right? So what can we do instead? Any idea? Any guess? In order to get some sort of limit of these distance functions, how can we get a limit out of these? So we have this distance.
Divide by something like growth and then take limit or something of the ratio.
No, dividing will not give you anything good because, look, if I take any 2 points, right, say Q and a Q prime, right?
Yes.
Okay,
Yes.
then, I mean, see, by triangle inequality, the distance from P to Q, right? This minus the distance from P to O, this distance is T, right?
Yes.
Okay. So this dPQ minus dPO, right? By the triangle inequality, this is less than or equal to the distance from Q to O, right?
Yes.
Right. So what does that mean? That means dPQ minus dPQ prime, this is less than or equal to dQO plus dQ prime O, right?
Yes.
So what now? Q and Q prime are fixed, right? Q and Q prime are fixed. So that means that this dPQ is equal to dPQ prime plus a big O of 1, something bounded. So if I divide by, if I rescale, if I divide by something, then I'll just get 1 on both sides, you see? I'll get a constant. I'll get a constant. If I try to rescale by dividing, I'll get a constant. So
Not-
dividing is not the right thing to do.
Hmm.
Dividing is not the right thing to do. What is the right thing to do?
Take the difference.
Subtract. Instead of dividing, you subtract the distance from P to O. Okay. So you consider the function, say, I don't know what to call it, say f sub t of q. This is d sub p of q minus d sub p of O. Okay. All right.
Okay.
Where this P is equal to gamma T. Okay. Now, by the triangle inequality, these functions are uniformly bounded on compacts, right?
Yes.
F sub T uniformly bounded on compacts. And in fact, it's easy to see by triangle inequality that because gamma is a geodesic, these functions are in fact monotone increasing. This is increasing in T. Therefore, it's bounded monotone increasing, it converges to a limit. Okay. So that limit will be a Boseman function associated to the geodesic ray gamma. So I'll say more about this in the next session. Let me stop here. We're out of time, so let me stop. Okay, so actually to see this is monotone increasing is very easy. It's just the triangle inequality. So so wait, what is this? This actually, this is nothing but TPQ minus T, right? Okay, because distance from P to O is just T. Okay, so yeah, to see monotone increasing, so this is the origin, this is Q, and now I take say an S, and it, so I mean gamma S and gamma T, right? Okay, so what am I looking at? I'm looking at the distance from gamma T to Q minus this distance, and I'm also looking at the distance from gamma S to Q minus this distance, right? So if I look at FTQ minus FSQ, right? So suppose S is less than or equal to T. Let me look at FTQ minus FSQ, right? I have to show this is greater than or equal to 0, right? Yeah.
Yes.
So what is this? Well, FTQ means I have a plus on this side, right? And then I have a minus and a minus here, right? This is FTQ, yes? And then I'm subtracting FSQ, right? So because I'm subtracting FSQ, what will I get? I'll get a minus here and a plus here. So this plus minus will cancel out. And I'll just get, oh, well, this is not increasing in T, sorry. It'll be decreasing in T. My bad, I'm sorry. This will be decreasing in T. I'm sorry. This will be decreasing. So this will be what? This will be just, I'll get this triangle, right? A plus and a minus here, right? This is gamma S. This is gamma T. This is Q, right? So this is less than or equal to 0 by the triangle inequality. right?
Yes.
So that means it's decreasing in t, right? So therefore it converges to a limit. It's bounded, so it converges to a limit. Is this all right?
Yes, sir.
Yes, sir.
So the Boseman function associated to the ray gamma is, so B sub gamma of Q, this is defined to be limit t tends to infinity, f sub t of Q. So f sub t of Q, this means basically just d sub gamma t of Q minus d sub gamma t of O. Okay. Is this all right?
Okay.
Okay. Now, the level sets of the Boseman function, what will they be? Well, what are the level sets of these functions ft? Well, the level set of ft will be basically spheres around gamma t, right? There's spheres around gamma t. Because I mean, this f sub t is just the distance function from gamma t minus a constant, right? So they have the same level sets, right? They have the same level sets. Yes. So the level sets of this function, here the level sets are spheres. Level sets are spheres around gamma t.
Okay, so the level sets of Boseman function will be Hurst spheres.
Right. So what happens is, as the center of the sphere goes off to infinity, in the limit, you'll get these spheres will converge on uniformly on compacts. These spheres will converge, well, Gromov-Hausdorff converge or whatever notion of convergence you want, they will converge to level sets of the Boseman function. Those are defined to be horospheres. So if you do this in the unit disk, in the H2, in the Poincare unit disk, you'll get Euclidean spheres which are almost tangent to the boundary. In the limit, they become tangent to the boundary. All right?
Yes.
Okay, so those are horospheres. So here, level sets, in this case, are defined to be horospheres. I mean, horospheres by definition are level sets of Boseman functions. Okay? Is this all right?
Yes.
Yes.
Yeah. So example, if you do this in the upper half plane, that's R cross 0 infinity. Then what happens is, if your gamma t is this imaginary axis, this is gamma. So if this is gamma t, you look at the sphere of radius t around gamma t. This is, say, gamma 0. So the spheres will be larger and larger Euclidean spheres. Okay. In the limit, they will converge to horizontal lines. Okay.
Yes.
So the horospheres in this case will be horizontal lines. These are horospheres based at infinity. Okay. Now, Utsav, you were asking about the curvature, right, of the spheres. So, well, what is this Hessian comparison theorem saying for large radius? For large radius, it's saying that the curvature of the spheres is bounded below by a positive constant, right?
Yes.
So that means in the limit, when you pass to the limit, the spheres converge to horospheres. And the convergence is actually C2. That means these functions f sub t, okay, these functions f sub t actually converge in C2 norm on compacts to the Boseman function. Okay. They actually converge in C2 norm on compacts. All right. So that means the Hessians converge. Okay. So the Hessians converge. So what happens is that nabla squared ft, this is the same as nabla squared d gamma t because they just differ by a constant. So this converges to the nabla squared of the Boseman function. Okay. All right. So what does that mean? That means the Hessian of the Boseman function will satisfy this estimate, right? Okay. So, and the Hessian of the Boseman function, like for the spheres, the Hessian of the Boseman function, the gradient vector field of the Boseman function will be the unit normal vector to the horospheres. Okay. So, in this picture, these are horospheres. And so the gradient vector field of the distance function was, they were normal to the spheres. So when you pass to the limit, the gradient vector field of the Boseman function will be normal to the horospheres. Okay. So this is the unit normal to the horospheres. And the integral curves of the gradient vector field for the distance function, those were geodesics starting from gamma t. In the limit, the integral curves for the gradient vector field for the Boseman function will be geodesics which meet at the same point at infinity. Okay, these are the integral curves of the gradient vector field. These are geodesics which meet at the same point at infinity in backward time. And these are perpendicular to the horospheres. Is the picture clear?
Yes.
Okay. So grad B gamma equal to outward unit normal to horospheres. So let me call it the horosphere H. Okay, and similarly, like we did for the distance function, the Hessian of the Boseman function restricted to the tangent space to a horosphere, this is equal to the shape operator of the horosphere. All right. From TQH to TQH. Is this clear? And A norm W squared is, by passing to the limit, you get this estimate. This is less than or equal to inner product TWW less than or equal to B norm W squared for all W in TQH. Is this okay?
Yes.
Yeah. So. So,
Sir,
yes,
this Hessian comparison theorem also gives us that the spheres in Hn are actually Euclidean spheres, isometric to Euclidean spheres. Because the
no.
principal curvatures are all one, right?
Right. Okay. Isometrically, abstractly. Yeah, that's true. That's true. In HN,
Yeah,
in real hyperbolic space. Yeah, that's
yeah,
true.
yeah.
That's
I
true.
haven't seen this otherwise. I mean,
That's true. That's true. That's true. Yeah, yeah.
don't know. Sir.
No, you're right. You're right. That's true. Because there,
I mean,
the Hessian,
I just guessed it here only. I mean, I haven't
yeah, no,
seen
the
other
Hessian,
proofs of this. I mean, this
the
HN,
Hessian
the
comparison
spheres
tells
in
you.
Hn will be Euclidean spheres that I haven't seen anywhere. I mean,
No, see, it just tells us, it doesn't say that there will be many Euclidean spheres in the ball model or the upper half space model. It does not tell us that. What it tells us is that the Hessian is constant, because here in HN, A will be equal to B. So
Right.
both left-hand side and right-hand side will be equal. So you'll get an equality for the Hessian, right? So that means the Hessian at each point will be a constant multiple of the identity, right?
Yes.
Yes. The Hessian at each point will be a constant multiple of the identity.
Yes.
So, yeah, that.
So the shape operator will be constant. Identity.
It will be identity at each point. That's
At each
true.
point.
Yeah. No, that does not tell us that. No. No, it does not tell us even that it's isometric to a Euclidean sphere. Abstractly isometric. No, even that it does not tell us. No, it does not. Okay, see. Okay, so fine. Look, another way of understanding curvature of a submanifold is how far it deviates from being geodesic. That means that, well, let's look at the example of spheres, right? Okay, so see, first of all, if I look at the Hessian of a function, yeah, so say Hessian of a function f acting on a vector v. What is this? This is so. Okay, let me look at the quadratic form. Sorry. So, okay. Well, okay. Let me start this way. So, suppose f is a function on M, a smooth function on M. Okay, and say Q is a point in M, and say V is a tangent vector at Q. Okay, and then let me take gamma to be a geodesic with initial velocity Q. Okay, sorry, V. So gamma 0 is Q, and gamma prime 0 is V. Okay, then let me look at the function f composed with gamma. Okay, so what is ddt of f composed with gamma? This is equal to, by the chain rule, df at gamma t applied to gamma prime t, right? Yes, this is the chain rule. So by definition of the gradient vector field, this is the same as inner product of the gradient vector field of f at the point gamma t, inner product with gamma prime t, right?
Yes.
Okay. So now if I differentiate again, suppose I look at d squared dt squared at t equal to 0 of f composed with gamma, then this is going to be what? This is going to be ddt at t equal to 0 of inner product nabla f gamma t gamma prime t, right? So by the Leibniz rule for the inner product, right? By metric compatibility, this is going to be the covariant derivative of this, of the gradient vector field, right? Capital D dt of grad f, right? Along gamma, right? Inner product with gamma prime 0 plus inner product nabla f at q with ddt t equal to 0 of gamma prime, right? Yes.
Yes.
But now gamma is a geodesic, so this second term vanishes, right?
Yes.
Because gamma is a geodesic. Okay. So what remains is just now this capital ddt of nabla f along the geodesic gamma. This is the same as just nabla gamma prime 0 of nabla f, right? Inner product gamma prime 0, right? Yes?
Just the Hessian of.
Which is exactly just the Hessian. So this is nabla squared f of v comma v. Okay. So we get another interpretation of the Hessian. The Hessian nabla squared f of v comma v is just the second derivative along geodesics. D squared dt squared at t equal to 0 of f of gamma t. Is this clear? Okay. So be careful. This is only for the second derivative along geodesics, not along other curves, right?
Because then the second term won't vanish.
Yes. If you do it on a curve which is not a geodesic, this term may not vanish, right? This ddt of gamma prime. So this is only the second derivative along geodesics, all right?
Yes.
So this is like the formula we proved in the first part of the course for Euclidean space, right? The Hessian, the second derivative of a function on Rn evaluated, so it was a symmetric bilinear form, evaluated along the diagonal. It was just the second derivative of the function along a straight line, right? The point is that straight lines in Rn are geodesics in Rn, right? So that generalizes to a general Riemannian manifold. The Hessian is just the second derivative along geodesics. Okay.
Yes.
Now look at the Hessian of the distance function. What does it mean then? Now consider, so P and M, Q and M minus P, W in TQS, S is equal to the sphere SPR, R is equal to the distance PQ. Okay, and let me choose gamma a geodesic such that gamma 0 equal to Q, and gamma prime 0 equal to W. All right. So what is the picture? I have this geodesic sphere. I'm taking a tangent vector W and a geodesic. Well, okay. So it's a bad picture. This is W, and this is a geodesic, gamma. Okay, this is the point Q. This is P. So what am I looking at? I'm looking at the second derivative of, so nabla squared dP of WW. This is equal to the second derivative, right? D squared dt squared at t equal to 0 of dP of gamma t, right? Yes?
Yes.
Now, in this picture, what is this second derivative? So let me blow up this picture. Let me zoom in near this point. What am I looking at? So magnify this. So when I zoom in, what I'll see is something like this. So here is the sphere which is bending like this. Okay. And here is the geodesic, which is going like this. And I'm looking at the distance. So this is the geodesic going to Q, and this is the geodesic going to gamma t. This point is gamma t. Okay, and this point is gamma 0, which is Q. Okay. Now, what is the second derivative? Well, see, this geodesic, this is tangent to the sphere, which is a level set of the distance function, right? So that means up to first order, the change in the distance function is 0 up to first order along this geodesic, right? Because it's tangent to the sphere, right? So this, what will the second derivative be? It will be basically this little distance here, this distance, you see, between the geodesic and the sphere. Okay, that is the second derivative, is this distance here. Do you see? Well, this distance, what will this be? This is basically, this distance is what? This is, see, the distance, P is somewhere out here. P is out here. The center P is out here. Okay. So this distance is the radius R. This is R. And this thing is, this whole distance is dP of gamma t, right? So this little distance, this is dP gamma t minus R, right? Which is equal to dP gamma t minus dP gamma 0, right? Now you do a second order Taylor expansion. So the first order term vanishes, right? Because, so this is what? T into inner product grad dP at Q with W, right? Plus half T squared into the second derivative, which is the Hessian, nabla squared dP WW, plus little o of T squared. Is this clear? I've just done a second order Taylor expansion of this function, dP composed with gamma. Is this clear? So this first term vanishes, right? because grad dP is perpendicular to W. This is 0.
Yes.
Right.
So what remains is this. So this little error here, this is basically half T squared into the Hessian. Okay, so the Hessian is basically giving you the divergence of the sphere from being geodesic. Do you understand? It's telling you how fast the geodesic is diverging away from the sphere, right? This little distance. That's the Hessian. You understand? So if the Hessian is 0, that means up to second order, the geodesic is staying inside the sphere. Got it? If the Hessian is positive, then that means the geodesic is going outside the sphere. If the Hessian is negative, then the geodesic is going to go inside the submanifold. Do you understand?
Yes, sir.
Yes, sir.
Okay. So that's why it's a measure of curvature, right? The Hessian, because it's telling you how far you are from being straight. Being straight means being geodesic, right? So this is giving you the deviation from being straight. Does it make sense?
Yes, yes.
Okay. So this little thing, this is nothing but T squared times the Hessian. So yeah, geometrically, this little difference, this is the Hessian. Okay, this is the Hessian. This into 1 plus little o of 1. There's a half T squared there. Okay.
Yes, sir.
All right. So fine. So we've said enough about curvatures and Hessians and so on and horospheres. Now I can come to what I was, the little note I sent you about the roots in a symmetric space, in a semi-simple Lie group. And yeah, so, okay, wait. All right, fine. Okay, so now, yeah, before getting there, let me just define something called the geodesic involution. So this is defined on any geodesic ball in a Riemannian manifold. So suppose B equal to BPR. So this is the image under the exponential of a ball of radius r around the origin. Okay, so this is suppose a geodesic ball in my Riemannian manifold M. Then we can define the following. So you take the tangent space, so from the tangent space to the tangent space, I have a map which is just reflection through the origin from TPM to TPM. V goes to minus V. Okay. Here's 0. Here's V. It goes to minus V. Okay, I have this reflection through the origin in the tangent space. Now I have the exponential map, which maps this ball in the tangent space to a geodesic ball in my manifold. Okay. Okay, so maybe the geodesic ball looks something like, I don't know, something like this. So yeah, so this is, well, so actually this should be, instead of TPM, I take B0R, not the full tangent space, I just take the ball here. Okay, and then I have the exponential mapping. So this is the diffeomorphism. So I can conjugate this map here, V goes to minus V. I can conjugate it to get a map from the ball to the ball, right?
Yes.
Okay. So so what will the conjugate? So let me call this map I sub P. This will be my geodesic involution. So what does it do? It maps X of V goes to X of minus V. Is this clear?
Yes.
So what does it mean? It means basically I take a geodesic passing through P and then I go a distance T along it. So if this is gamma T, then this I map to the point going backwards along the geodesic, gamma minus T, right?
Yes.
Okay. So this is the geodesic involution. All right. Now, this I can define on any geodesic ball. Okay. But then there are questions. This, first of all, this is just a diffeomorphism from the ball to the ball, this geodesic involution. Okay. So this I sub P from B to B is called the geodesic involution at P or through P. Yeah. Now, this need not be an isometry. Okay. And also, this need not extend to a diffeomorphism of the whole manifold. So for example, if I do it on a surface of genus 2 like this, right? So here I have a geodesic ball, right? So my geodesic involution is defined on this ball to itself, but you can see I can't extend it to a diffeomorphism from the surface to itself. That won't happen. Okay. Do you understand? If I try to extend this ball, it's not going to, I'm not going to get a diffeom, it's not going to extend to a diffeomorphism from the manifold to itself in general. Okay. So this does not extend to a diffeo from M to M in general. Okay, can you see that in this picture? Yeah. Okay. If I try to grow this ball, I'll run into problems, right? After some point, it's no longer a ball. And yeah, it won't be well defined. So. You see, I mean, given a point here, there are going to be many geodesics starting from here, which land up here. There'll be a geodesic like this. There'll be a geodesic also which goes back around and comes like this. So how do I define the geodesic involution in this case? Do you understand?
I mean, like the moment we run out of the little radius, we get into problem. That's what you're saying.
Yes, yes, essentially, yeah. Okay, so it does not extend to a diffeomorphism in general. There are some special situations where it does. So for example, if I take a flat torus, not just any torus, but a flat torus, R2 mod Z2, in this case, it does extend. In this case, it does extend. Even though the exponential map is of course not injective, but it's still, it does extend. In this case, it does extend. Okay, in this case, it will extend. It's just the map, I mean, x goes to minus x from R2 to R2, that sends the lattice to itself. Therefore, it descends to a map from the torus to the torus, right?
Yes.
So in this case, it will extend. Okay. Okay. Now, yeah, so I should just mention one remark. This geodesic involution, it fixes the point P. And as you can see, the derivative of the geodesic involution at the point P is minus the identity from TPM to itself.
Yes.
Okay. Okay. So let me stop and we'll start another session.
So maybe after 1 minute.
Yeah, sure. Take a break. Yeah. Okay. After a 2-minute break. Yeah. Okay. Okay. Okay, so now I think we can, so we've defined the geodesic involution on any geodesic ball in a Riemannian manifold. So of course, if the manifold is a Hadamard manifold, then the exponential map is a diffeomorphism from the whole tangent space to the whole manifold. So then the geodesic involution is a diffeomorphism from the manifold to itself, right? In that case, the geodesic involution is a diffeomorphism of the whole manifold. So it extends everywhere, but it may not be an isometry. Okay. So a symmetric space is a very special Riemannian manifold where for each point, the geodesic involution, it not only extends to the whole manifold, but it is also an isometry. Okay. So here I've defined it to be the following. For every
what happens
Yes.
in locally symmetric spaces?
So that's what I was saying. In locally symmetric, in this picture, you take this here in this genus 2. This is locally symmetric, right?
Okay.
This is
So it happens locally.
Yeah, so the geodesic involution is only defined on a ball, on a geodesic ball, but it doesn't extend to a diffeomorphism from the whole manifold to itself, right?
Okay.
Because it won't be well defined, because you want to send v to x minus v. The problem is the exponential map is no longer 1-to-1, right? So, I mean, this point will be the image under the exponential of actually infinitely many points. So the geodesic involution will not be well defined. It will become multi-valued. It won't be well defined. It will have singularities when you try to extend it. Does that make sense? Yeah.
Yeah. Okay.
So for a globally symmetric space, it's okay because the exponential map is a diffeomorphism. So yeah. Well, I mean, that's if it's of non-compact type. If it's of compact type, then it's true like for the compact symmetric spaces. So S2 here for every point, the geodesic involution is just, it's well defined here. So yeah, so for some for symmetric spaces, I mean, by definition, for a symmetric space, the geodesic involution, which initially is only locally defined in a geodesic ball, it extends to a global diffeomorphism of the manifold, and that diffeomorphism is an isometry. So symmetric spaces are very special in this sense. Is that okay, Rudrada? Any question? Yeah.
Yes. Yeah.
It's okay. Yeah. Okay. So So for a symmetric space, for every point P, we have an isometry I sub P from M to M, which fixes the point P and whose derivative at the point P is minus the identity, okay, from TPM to TPM. So notice this actually, these two conditions, that it fixes P and that its derivative at P is minus identity, these two conditions determine this. I mean, if there is such a isometry, then it is unique. Okay, there is a unique such isometry satisfying these two conditions. Because if you have two such isometries, say F and G, you look at, let's say, F composed with G inverse, then that will fix P and its derivative at P will be the identity. And then it's easy to show for any complete Riemannian manifold. If an isometry fixes a point and its derivative at that point is the identity, then the map is the identity, right? Because if the derivative is the identity, then, I mean, geodesics passing through P are going to go to geodesics passing through P. And since the derivative is the identity, the initial tangent vector of the geodesic will go to itself. So that means geodesic passing through P will go to geodesics passing through P. And because it's an isometry, it will preserve the distance along the geodesic. And that means every point will be fixed along the geodesic, right?
Yes.
Yes, sir.
For this argument, I just need a connectedness, right? The completeness is not necessary.
I guess, yeah, you don't, well, you know, you need completeness because you want to say that the exponential map is surjective, right? For that, you need completeness.
Okay.
I mean, for example, just take.
No, I was just recalling that you were just citing that problem, right? Referring to that problem that if.
Oh, actually, no, you're right. You're right. You just need connectedness. Actually, you just need connectedness. Yeah.
Yes, yes.
That's true. That's true. You can, I mean, no, what I was thinking is basically you take R2 minus a segment, right? Then if I look at the exponential map from here, I don't have geodesics which come here, right? From starting from this point, there's no geodesic coming here. So it's not complete, right? So the exponential map is not surjective. But what I can say is basically I can go from here to here, right? And over here, the map will be the identity in a neighborhood here. And then from here, I can do the same argument. And then I'll get the map is identity in a neighborhood here. You see what I mean?
Yes.
Okay, so this I can do. Yeah, so you just need connectedness. You're right. You're right. Yeah, you just need connectedness. Yeah. Okay. Okay. All right, so we have this geodesic involution, which is an isometry for a symmetric space at each point, I sub P. Okay. And so if I look at I sub P squared, then its derivative at P is equal to identity. So that means I sub P squared must be identity, right? Okay. So it's an involution. And as you see in this picture, if I take a geodesic gamma passing through P, then it sends gamma t to gamma minus t, and gamma minus t goes back to gamma t. So it's a reflection through the point P. Okay. All right. Now suppose I look at so I can look at the derivative of IP, right? So that's going to be a map going from the tangent space at gamma minus t to the tangent space at gamma t, right? So the claim is that this map is nothing but minus parallel transport along the geodesic gamma. Okay. So why is that? So take a vector field V, which is parallel along gamma. Okay. And let's call this map IP just I. Okay. So let me define a new vector field V tilde by basically applying the isometry I to the vector field V. Okay. So that means V tilde of t is going to be, so V tilde of t is a point at, is a vector at gamma of t. So how do I get this vector at gamma of t? What I do is I look at V at the point minus t. So that's a vector at gamma minus t. Then I have the derivative of IP acting over here. So it will send a vector at gamma minus t to a vector at gamma t. Okay, so that's what I do. I apply the derivative of I at gamma minus t to v minus t. Okay, this gives me a vector at gamma t. Is this clear?
Yes, sir.
Yes.
Yeah. Like in this picture. Now, because I is an isometry and V is parallel, applying I to a parallel field will send it to a parallel field. Okay, that's easy to see. Yeah.
Yes.
Okay, so therefore V tilde will become parallel along gamma as well. Okay, but now if I look at the point P, which is fixed by I, then at this fixed point, V tilde 0 is equal to minus V0, right? Yes, because the derivative of I at the
Yes.
fixed point is minus identity.
Right.
So V tilde 0 is minus V0, but now both of these are parallel vector fields, right? So if at one point V tilde is equal to minus V, then at all points V tilde will be minus V, right? Yeah.
Yes.
By uniqueness of parallel transport, if two parallel fields agree at a point, then they agree everywhere, right? By uniqueness of parallel transport, right? Is that clear?
Yes, yes.
Yes, Utsav?
Yes, sir.
Okay. So that means V tilde is minus V for all t. What does that mean? That means that this V tilde is minus V, right? So that means that, I mean, V over here is given by parallel transport of V over here, right? But V tilde is minus of V. So that means that, and V tilde is given by applying the derivative of IP. That means the derivative of IP is minus parallel transport. Is this clear?
Yes, sir.
Okay. So this derivative of I at gamma minus t, this is minus parallel transport from gamma minus t to gamma t. Okay. All right. So we've got something about this derivative of the this involution, the geodesic involution. Now we can use this to construct the following isometries which preserve a geodesic. So suppose gamma is a geodesic in a symmetric space. Okay. And I take 2 points, say gamma 0 and gamma t are my points P and Q. What I do is I divide up the interval from P to Q into 4 equal parts. Okay, so this distance is T by 4, T by 4, T by 4, T by 4. Okay, now around X, I have a geodesic involution IX, and around this point Y, I have a geodesic involution IY. I define AT to be the composition IY composed with IX. Okay. All right. So what is this going to do? It's going to send P to this midpoint, and then this midpoint will go to Q, right? So P will go to Q. Is this clear?
Yes.
Right? Yes. Okay. And it's clear it's going to preserve this geodesic. This geodesic is going to go to itself, right? Because IX preserves this geodesic since this is a geodesic passing through X, and IY preserves this geodesic because it's a geodesic passing through Y. So therefore this AT, this is going to preserve this geodesic, right?
Yes, sir.
Yes. And it maps gamma 0 to gamma t, and it's an isometry of this geodesic. Therefore, it's going to map every point gamma s to gamma s plus t, right? Okay.
Yes.
Okay. So this is a isometry which preserves this given geodesic gamma. Okay. And what is the derivative of this AT? Well, it's going to be by the chain rule, the derivative of IY composed with the derivative of IX, right? Now, what is the derivative of IX? This is minus parallel transport from gamma 0 to gamma t by 2, and then composed with minus parallel transport from gamma t by 2 to gamma t, right? So therefore, the composition just becomes parallel transport from gamma 0 to gamma t. Is this clear?
Yes.
Okay. So in a symmetric space, what we're seeing is that so if M is a symmetric space, and gamma is a geodesic in M, a bi-infinite geodesic, then suppose PT is parallel transport from gamma 0 to gamma T. Okay. Then what we've shown is that then there exists a unique isometry such that AT of gamma 0 is gamma T and DAT at gamma 0 is equal to PT. Is this clear?
Yes.
Okay, the uniqueness given these two conditions is by the same argument as before. For unique, which was the argument for uniqueness of the geodesic involution, right? It's the same argument. Okay. All right.
Yes.
And note that you see parallel transport, if this is gamma 0, this is gamma whatever S, and this is gamma S plus T. Right, so here I have a parallel transport map, PS, and here I have another parallel transport map, PT. Okay, and the composition I know is parallel transport PS plus T, right? Yes?
Yes, sir.
So PS plus T equal to PT composed with PS. This implies that by uniqueness of these isometries AT, that AS plus T is equal to AT composed with AS. Is this clear?
Yes, sir.
Okay. Yeah. So we get a, so basically what we're doing is we have these parallel transport maps between the tangent spaces along the geodesic. Those extend to isometries of the whole manifold. And then because parallel transports form a group in a sense, the corresponding isometries, they form a one parameter group. All right. Okay. So this gives us a one parameter group AT along any geodesic, which preserves the geodesic. All right. Okay. Okay. So, for example, in the upper half space, hyperbolic upper half space, right? This, if I take the geodesic gamma to be the imaginary axis, the vertical geodesic from the origin, then this AT is nothing but multiplication by e to the t. Okay. All right.
Yes, yes.
And what are the orbits of this group AT? They are straight lines through the origin, right? In the upper half space. Okay, the orbits are straight lines through the origin. So if I look at it in the ball model, well, then the orbits, exactly only one orbit is a geodesic from the North Pole to the South Pole. all the other orbits are, well, they're not geodesics, okay? There's some curves from North Pole to South Pole. Exactly one orbit is a geodesic. Is this clear?
Yes.
Okay. Yeah. Okay, so this is the orbits of AT. Okay, now once I have a one parameter group of diffeomorphisms, I can differentiate them with respect to T to get a vector field, right? So I get a vector field H. H of X is what? It's ddt at T equal to 0 of ATX. All right. So this gives me a vector field H on my symmetric space. All right. Okay. Now in my symmetric space, we know that we have this nil from the Iwasawa decomposition. We have the nilpotent group N acting on my symmetric space by isometries. And we know that the N orbits are horospheres. Okay, we've already defined horospheres, right?
Yes. The levels of the Boltzmann function.
Yeah, level sets of the Boltzmann function. Okay, so now let me take so gamma to be this the AT orbit of the origin. So that's a geodesic. So this is the gamma. And now let me take sigma to be the N orbit of O. So that's the horosphere passing through the origin, which is perpendicular to gamma. Okay, so this is sigma. All right. This horosphere is sigma. Okay. So now let me take a vector W, which is tangent to which is in the Lie algebra of N. So that's little n. Okay, Lie of capital N. So this Lie of N is identified with the tangent space to the horosphere at the origin, right? Okay. Yes.
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 All right. Okay. So now I take N sub S to be the one parameter group defined by this W. So this is not e to the T. This is a typo. This should be e to the SW. Sorry. This is e to the SW. Sorry. Okay. So this is a isometry. So N sub S. Okay. Now I can apply this isometry to the geodesic gamma. So I get a new geodesic gamma S is equal to NS composed with gamma, right? So this gives me a one parameter family of geodesics, gamma S, right? So I get a parameterized surface, f of st is equal to nsat dot o, right? Which is equal to gamma S of t. Is this clear? So now this one parameter group ns, this also gives me a vector field. Let me call that W. So W of X is dds at S equal to 0 of ns dot X. Okay. So this is also a vector field W on M. And this one parameter family of geodesics. So this is gamma S, you can see. Okay. These gamma S's are all perpendicular to the horospheres. Okay. And they all have the same starting point at the boundary. Okay. So when I differentiate a gamma S with respect to S, I'll get a Jacobi field J along gamma, right? Yes?
Yes.
Okay. Right. I have a one parameter family of geodesics. So when I differentiate, I'll get a Jacobi field. And that Jacobi field is nothing but the vector field W on M restricted to gamma, right? Yes? Okay. Because what is J of T? It is del S at S equal to 0 of gamma S of T. This is a Jacobi field, and it will be a normal Jacobi field also. And this is del S at S equal to 0 of ns dot gamma T, right? And differentiating with respect to S, ns dot anything gives you W of that, right? So this gives you W of gamma T. Is this okay?
Yeah.
So restricting W to the geodesic gamma gives you a normal Jacobi field J. Okay. Now, if I take a point P on the geodesic gamma, let me look at the bracket of these two vector fields, H and W, at the point P. Okay. So remember, the Lie bracket is the same as the Lie derivative, right? right? Lie bracket is the same as the Lie derivative, right? LH of W. Now, what is the Lie derivative? The Lie derivative means I have to look at W along the integral curve of H. So that is ATP, right? And then I have to pull back by the inverse of the derivative of the flow of H, right? So that will be DAT inverse at AT of P, right? Yeah, this is by definition the Lie derivative. Yes, Orkojit, Utsav?
Yes, sir. Yes.
Yes, sir. Fine. Yes.
Yeah, this is the definition of the Lie derivative. But
Right.
now what is the derivative of AT? This we have seen, this is the inverse of parallel, I mean, this is parallel transport. So this is pulling back by parallel transport, right? Okay. So this is DDT of PT inverse of W of ATP. But I know that differentiating a vector field, I mean, by by pulling it back by parallel transport, that's the same as the covariant derivative, right? This is just capital DDT of W.
Yes, yes.
So this is nothing but nabla sub H of W, right? Is this clear?
Yes, sir.
Yes.
Okay, so that means along the geodesic gamma, the Lie bracket HW is equal to nabla H of W. Okay. Okay, but now what is nabla H of W? So this is, the covariant derivative of W. So this means capital D del DDT of del del S. And what is W? W is del del S at S equal to 0 of gamma S of T. So now I can use symmetry of the connection. So this capital D del T and del del S, I can interchange these two. This becomes capital D del S at S equal to 0 of del del T at T equal to 0 of gamma S of T, right? And del del T at T equal to 0 of gamma S of T is what? It's gamma S prime 0, right? This is gamma S prime 0. And what is gamma S prime 0? So gamma S was this geodesic. So gamma prime is perpendicular to the horosphere. Gamma S prime is also perpendicular to the horosphere, right? And so this is nothing but the outward unit normal to the horosphere. Okay. So what is this? This is D del S of the normal N of gamma S of 0, right? Gamma S, yeah, N of gamma S 0. Is this clear?
Yes.
Okay. So in other words, this is the covariant derivative of the normal, the outward normal in the direction of W, right? Because I'm differentiating D del S, this del del S of gamma S 0 is just W, right? If I differentiate with respect to S, I get the vector W. So this becomes nothing but nabla W of N. Is this clear?
So it's just a shape operator.
Which is exactly the shape operator of the horosphere. Which is exactly the shape operator of the horosphere. Okay, so finally, what do we get? We get that if I look at the map add H, so this goes from little n to little n, W goes to bracket of H and W. When I identify little n with the tangent space to the horosphere, then this add H is nothing but the shape operator of the horosphere. W goes to nabla sub W of N, where N is the outward normal. Is this clear?
Yes, yes.
Okay. So now
Yeah.
what are, Orkojit, is this all right?
Yes, sir. Fine.
Rudroda, is this okay?
Yeah,
Yeah.
yes.
So add H is nothing but the shape operator of the horosphere. And so now what are the roots alpha I? These are the eigenvalues of add H, right? Restricted to N. So those are nothing, I mean, those are the positive roots. So those are nothing but the eigenvalues of the shape operator, right? Because add H is the shape operator. And so these are the
Yeah.
principal curvatures of the horosphere. Okay, these are the principal curvatures of the horosphere. Okay, so the roots geometrically, these give you principal curvatures of the horosphere. All right. And 2 rho, which is the sum of the roots, is the sum of the eigenvalues. That's the trace of the shape operator. So 2 rho is a trace It's the trace of the shape operator, which is the, so the sum of the principal curvatures is called the mean curvature, okay, for any submanifold. So the 2 rho is the mean curvature of the horospheres. Okay. And finally, for another geometric interpretation, if I take, say, n to be an eigenvector of add h, okay, with eigenvalue alpha. So that means h bracket n is equal to alpha n. Then what does that mean? Then along gamma, nabla sub h of n is, this is equal to bracket hn. This we already showed, right?
Yes.
So that means that nabla sub h of n is equal to alpha n, right? I'm assuming that n is an eigenvector of add h. So that means nabla sub h of n is alpha n. Okay. So now if I let J be the Jacobi field, which is n restricted to gamma, right? I know that this is a Jacobi field, right? Then nabla sub h of n, this is nothing but dj, capital D dt of j, right? Yeah, because h is tangent to the geodesic gamma. So this nabla sub h of n is just dj dt, right?
Yes, yes.
So then I get that dj dt is equal to alpha j, right? So this means that if I put v to be e to the minus alpha t into j, then v will become parallel, right? Because dv dt by the product rule will be what? It will be minus alpha e to the minus alpha t into j plus e to the alpha t into dj dt. But dj dt is alpha j. So these two terms will cancel and I'll get 0, right? Is this clear? So v is parallel along gamma, right?
Yes, sir.
So what does that mean? That means that j is equal to e to the alpha t into v, right? So where v is parallel. Okay. So that means this this Jacobi field, as you can see in this picture, this Jacobi field, it grows exponentially at a rate alpha. Okay. So you see in this picture, this Jacobi field is growing exponentially at a rate alpha. All right. It's a parallel field into e to the alpha t. Okay. Is the picture clear? Yeah.
Yeah.
So now we know that j is e to the alpha t v, where v is parallel. So now I use the Jacobi equation. So I know that j double dash plus r of gamma prime j gamma prime, this is 0. So this inner product with the parallel field v is also 0, right? But now what is j double dashed? J is e to the alpha t v, where v is parallel. So j double dash will be alpha squared e to the alpha t into v, right? And what is this r of gamma prime j gamma prime? Well, j is e to the alpha t v. So e to the alpha t will come out and I'll get r of gamma prime v gamma prime inner product v, right?
Yes.
And here v is perpendicular to gamma prime. So this term will be nothing but sectional curvature k of gamma prime v into norm gamma prime squared norm v squared, right? So and here I'll get a v inner product v. So finally I'll get what? I'll get e to the alpha t into norm v squared coming out, and inside I have alpha squared plus sectional curvature k of gamma prime v, right? So this is equal to 0. And so I can cancel these two terms and I get that alpha squared plus this sectional curvature is equal to 0. In other words, alpha squared is equal to minus the sectional curvature of h and n, of the two planes spanned by h and n. Is this okay?
Yes, sir.
So, so the picture is that the picture is the following. You have yeah, maybe I can draw it in the upper half space model. Well, this is the NA model of a symmetric space, NAK. So M equal to NAK mod K, which is identified with NA, which is identified with some R to some capital N cross 0 infinity. Okay, so I have an upper half space model. So I have this geodesic. This is AT.O. Okay. This is my origin. And now what happens is I have these NIs. These are in little n. Okay. These are eigenvectors of add H. So here is my vector H pointing like this, and the ends are perpendicular to this. So I can have, let's say, an N1 like this, and maybe I have another perpendicular eigenvector like this, N2. Note that these eigenvectors are going to be perpendicular because they're eigenvectors of a self-adjoint linear map, right? The add H is the same as the shape operator, which is self-adjoint. So it has an orthonormal basis of eigenvectors, right? So I'll get these orthonormal NIs, okay? Is that clear? Yeah?
Yes.
And each of these will give me basically a two-plane. So this H and this N1, that will give me a two-plane. And it turns out if I take the exponential of that, that will be what's called a totally geodesic submanifold. So it'll look like this. Okay. And then if I take the exponential of these N2 and H, that will give me something looking like this. Okay. All right. Yeah. And what happens is that these totally geodesic submanifolds, this is what? This is a submanifold. What should I call it? So S. This submanifold is X of R. So SI. This is R NI direct sum R H. X of this dot O. Okay. This is a submanifold which will be isometric to H2, but not with constant curvature -1, with constant curvature K equal to minus alpha I squared. Okay. So that's what happens at each point. I have these constant curvature surfaces in these orthogonal directions around this geodesic. Okay. And each of them has constant curvature minus alpha I squared. Is the picture clear?
Yes.
Okay. So this is another geometric interpretation of the roots. Okay, their squares are minus the sectional curvatures in these directions, in these two planes. Okay, so.
And in the case of the real hyperbolic space, the boundary is commutative. I mean, yeah, so that's why we get the in all direction the curvature is equal. Unlike in the case of the complex hyperbolic space, we have Heisenberg group.
Yeah, for the real hyperbolic space, all the roots are equal. All the roots are equal.
Yeah.
Yeah, for the real hyperbolic space, the roots are equal. For complex hyperbolic space, you have roots 1 and 2. So when you square them, you get 1 and 4. And so then you have sectional curvatures in between -1 and -4.
Right.
That's
So these sheets you are taking, these are geodesically convex.
Yes, they're totally geodesic. Yes, yes, yeah. I can explain a bit more if you give me a 5 minutes, if you want. Otherwise, I can stop. You say what.
Sure, sure.
Yes,
Okay, then
fine.
I'll just explain 5 minutes. Okay, fine. So just one more session for 5 minutes. Okay, fine. Yeah, so just to finish the discussion, what happens is actually the following. So okay, so I have H, who's the H. Oh shoot! How did you become the host?
Sir, I don't know. Suddenly I misclicked somewhere. Yeah.
Oh,
I'll make it.
yeah, just make me the host.
So you have to allow Utsav to record. Oh, it's ready.
Recording is okay.
It's recording. Okay, it's recording. Okay, it's recording. All right, fine. Okay, so yeah, all right. So this is the orbit of e to the th, right? This geodesic. Now, if I have H. This is in script G, and I have say I take an Ni, which is in little n. Okay, so that bracket H Ni is equal to alpha Ni. Okay. Now I have my Cartan involution around this point, right? I. Okay. So this is an isometry. I have my geodesic involution, right? Okay, so this is an element of the isometric group, capital G. Okay. So what I can do is I can conjugate one parameter subgroups, right, by I, right? So I have this conjugation map, right? C. So I mean, look for any G in G, we have the conjugation by G from G to G. H goes to GH, G inverse, right? And then I look at the derivative. So this fixes the identity. So then you define big add of G, right? This is defined to be the derivative of this conjugation map at the identity, right? So this goes from the tangent space at the identity, which is fractal G to fractal G, right? So this goes from the Lie algebra to the Lie algebra, right? So this is the adjoint representation of the Lie group acting on its Lie algebra, right? Okay.
Yes.
Right. Okay. So what I can do is I have this Ni. Ni gives me a one parameter subgroup. The image of that one parameter subgroup here acting on the origin will be a curve in the horosphere like this. Okay. Yeah. And now what I can do is I can define Ni bar to be add I, the geodesic involution acting on Ni. Okay. I define this to be Ni bar. So this is just an element of the Lie algebra. Okay, so so this belongs to N bar, which is the add I of N. Okay. Now, what will this Ni bar do? Well, see, what will the geodesic infinity? You can see it in the picture what's going to happen. So I maps this horosphere to a horosphere like this, right? To a horocycle like this, right? I maps this horosphere to this horosphere, right? Okay. So maybe let me call this point 0 and infinity. Whatever. So I interchanges these 2 points of the geodesic. So it's going to map the horosphere based at infinity to a horosphere based at 0, right?
Yes.
Yes. And your e to the s ni, this is going to get conjugated by I to e to the s ni bar, right?
Yes.
Okay. Yes, Orgojit, is this all right?
Yes, sir. Sir, fine.
Yeah, Rudroda, is this okay?
Yeah, I think so. Yeah.
Right. Okay. So Ni, e to the s capital Ni is going to act on the upper horosphere. E to the s Ni bar is going to act on the lower horosphere. Okay. Because I mean, after all, I e to the s capital Ni I inverse, this is equal to e to the add I
Right.
Ni. Okay.
Yes.
Right. Okay. So that will tell you that you get this lower horosphere will be acted on by Ni bar. Now the point is that if I look at this R H direct sum R Ni direct sum R Ni bar, this is closed under Lie bracket. So this is a Lie subalgebra. This is the Lie subalgebra of
G.
bracket G. Okay, why is that? So I just have to check these brackets belong in the same. So first of all, H and Ni is fine. This, of course. So let me call this thing, I don't know what, let me call this H, okay? All right, so, yeah, okay. So this bracket, of course, this is alpha Ni, this is fine. This belongs to H. That's okay. Then I have to take the bracket of H and Ni bar, right? Now, what is the bracket of H and Ni bar? So how do I get this? Okay, so notice first that I conjugates AT to minus AT, right? I mean A minus T, sorry. Is this clear? If I go T along the geodesic and I conjugate by I, it's the same as going minus T, right?
Yes.
Okay, so I conjugates AT to A minus T. Okay, so this, when I differentiate with respect to T, this will tell me that add I of H is equal to minus H, right? When I differentiate with respect to T equal to 0, right?
Okay.
Yes. Okay.
Yes.
Just take ddt at t equal to 0, you'll get add I of H is minus H. Okay. So this H Ni bar, what is this? This is, I can write H as therefore minus add I of H, and Ni bar is add I of Ni. Okay. So this becomes, now add is a Lie algebra homomorphism. So I can take the add I outside. So this becomes minus add I of the bracket of H and Ni. Okay.
Yes.
And this is minus add I. So bracket of H and Ni is alpha I Ni. Right? So what does this become? Add I of Ni is Ni bar. So this becomes minus alpha I Ni bar. Okay, so this is also in H. Is this clear?
Yes.
Now the last thing I have to check is the bracket of Ni and Ni bar, right? Okay, the bracket of Ni and Ni bar, right? So what I can do is, let me apply add I to this. Okay, so add I applied to this is, since it's a Lie algebra homomorphism, this is, I can take the add I inside. Sorry. So I take the add I inside. Okay. And so add I applied to Ni will give me Ni bar. And applied to Ni bar, this is add I of Ni. So I get add I squared, which is add of I squared. I squared is identity. So add of I squared is identity. So this will just give me Ni, right? Okay. So this is minus bracket of Ni and Ni bar, right? Okay. So add of this vector is minus this vector. That implies it must be a multiple of H actually. Okay, the minus one eigenspace of add I is just H actually. It has to be a multiple of H.
Yes.
Okay. So this belongs to kernel of add I plus identity. And this is equal to RH, which is contained in my vector space H. Okay, therefore this is a Lie subalgebra, all right? Okay, and in fact, this is isomorphic to little SL2, right?
Yes.
In fact, this is isomorphic to little SL2. So this, well, with different constants, that's all right. Instead of, I mean, the usual presentation of little SL2, right? You have the three generators, H, N, and N bar. The bracket of H and N is, well, plus, I mean, 1 times N or 2 times N, depending how you write it, I think. I mean, in some books I've seen 1, in some I've seen 2. So, yeah. So anyway, so instead of 1 or 2, you have these roots alpha I here, okay? In general, you have alpha I's here. So for H and Ni, you have alpha I. For H and Ni bar, you have minus alpha I, okay? Right? So now this is a, so I get a Lie subgroup, therefore. So what should I call the subgroup? I don't know, just some name. I can't use H because H is already there. So I don't know, there's just some subgroup. So S is equal to, let me call it X H. This is a subgroup of G, okay, which contains e to the TH. And so now if I look at the image, so say I'm in the ball model. Okay. So I have my H and I have my Ni. And so that's going to, the image is going to give me like a disk like this, you see. A vertical disk in the middle. Okay. And this disk is totally geodesic, meaning that, Well, so look, this S, this acts transitively on its image in the symmetric space. So that is, so let me call that sigma. This is S dot O. Okay, so this thing is sigma. Okay, this is H, this is Ni, right? And yeah, so so this S is isomorphic to SL2R, big SL2R. Okay. And now, how do I get geodesics? So I already have one geodesic passing through here, right? How do I get other geodesics? Well, this SL2R, this is what? This is, I mean, this is NAK, right? So where this contains a compact K, right? This contains SO2R. Okay, so I have an SO2R which will act by isometries on this. This SO2R, this will act on my submanifold sigma. You see, so by that will basically be rotations in this two plane. So by rotating, I'll get geodesics in all directions through the origin. All right.
Yes.
And now, once I've got geodesics in all directions through the origin, then just by translating by elements of S, I'll get geodesics through all points, okay, in all directions. So therefore, I'll get geodesics between all points in this submanifold, right? So this submanifold, therefore, will be totally geodesic. That is, any 2 points can be joined by a geodesic in it. Is this clear?
Yes.
Yeah. Okay.
Yes.
Because I started with this initial H geodesic, that was a geodesic in the whole space, right? And now I'm just taking translates of this by this group S, which is isomorphic to SL2R. And this SL2R preserves this sigma, this two-dimensional submanifold, right? And so therefore, the images of this initial geodesic under S, those will stay inside sigma. So those will give me geodesics of the whole space inside sigma, connecting any 2 points in sigma. Is this clear?
Yes, sir.
Yeah. Orkojit, is this clear? So this is geodesically convex, right? Makes sense?
Yes.
Yeah.
Yes. Yes.
Okay. Okay. So that's the picture. Yeah. So so I'll have for each eigenvector Ni, I'll have a geodesically convex copy of H2 basically, except the sectional curvature will be constant equal to minus alpha I squared. Okay. Is it clear now?
Yes, sir.
Yes, sir.
So this is the full picture. This is the full picture. Yeah. Okay, so I get all these copies of little SL2R for each eigenvector Ni, I get a copy of SL2R. And that gives me a totally geodesic copy of H2, except the sectional curvature is minus alpha I squared instead of -1 in general. That's all. Okay.
Okay.
Yeah. Any questions? Okay. Anyway, I just thought it would be nice to talk about symmetric spaces geometrically. That's all. So I hope it was useful. I mean, I don't know.
Yes, sir. Yes.
All right. Okay. So see you Thursday then. Okay. Thanks.